From a distance, our solar system appears as a quiet, orderly clockwork of planets in a dark, empty void. But at the center sits a raging, boiling sphere of plasma. As this diagram shows, if you take every planet, moon, and asteroid we know of and put them together, they account for less than 0.25% of the matter in our solar neighborhood. The sun holds 99.8% of all mass, wielding a gravitational grip that dictates the movement of everything around it. This immense mass gathered 4.6 billion years ago when a giant molecular cloud of dust and gas collapsed under its own weight. That initial collapse started a reaction that continues today. The sun is a continuous, contained explosion. The crushing inward force of its own immense gravity is locked in a constant, violent struggle against the outward thrust of nuclear reactions. To understand how we survive in the blast radius of this stellar engine, we have to look past the blinding light and travel directly into its crushing center to see exactly where that energy is born. Deep inside the sun's core, the conditions are incomprehensible. The temperature reaches 15 million degrees Celsius, and the pressure is hundreds of billions of times greater than the atmosphere on Earth. Looking at this cross-section of the core, we can see how this extreme environment forces hydrogen atoms to slam into one another. The gravity is so intense that the atoms fuse together to form a heavier element, helium. During this fusion process, a tiny fraction of the original mass is destroyed. Following Einstein's equation, E equals mc squared, that missing mass doesn't vanish, it converts into pure outward energy. But that energy cannot easily escape. As these newly born photons of light enter the radiative zone, they violently ricochet off densely packed plasma. A single photon can spend over 100,000 years trapped in this layer, zigzagging blindly toward the surface. Once the energy finally clears the dense plasma, it enters the convective zone. Here, the heat travels the rest of the way up by physically boiling toward the surface, much like rolling bubbles in a pot of boiling water. This obstructed journey serves as a buffer. Without the thousands of years of resistance provided by the sun's internal layers, the energy would be released in a singular, uncontrolled pulse, rather than the steady, life-sustaining stream we experience on Earth. After thousands of years, the energy finally breaks through to the photosphere, the visible, bubbling surface of the star. The surface is entirely dictated by intense, twisting magnetic fields. When these fields become tightly bundled, they block the rising heat, creating cooler, darker regions known as sunspots, labeled here in the upper and lower hemispheres. Above these dark patches, massive, glowing loops of superheated plasma arch thousands of miles into space. These solar prominences remain suspended, trapped within the invisible, twisting magnetic lines. Eventually, the tension in these tangled magnetic fields becomes too great. The lines snap, releasing the stored energy in a blinding burst of radiation, known as a solar flare. These surface anomalies act as pressure valves. When the magnetic tension finally breaks, it launches massive clouds of plasma directly into the vacuum, sending high-energy shocks across the solar system. This view from a coronagraph shows the ultimate release of that pressure, a coronal mass ejection, where an entire cloud of plasma completely breaks free from the sun's gravitational hold. During an event like this, the sun hurls billions of tons of electrified matter outward at speeds exceeding 1,000,000 miles per hour. Even when it isn't erupting, the sun emits a continuous wave of charged particles, known as the solar wind, hurtling outward in every direction. Energy born in the core has reached the vacuum as a physical, destructive wave of radiation. It carries enough kinetic force to strip the atmosphere off an unprotected planet. Earth survives this constant barrage only because of its invisible magnetic shield. When the solar wind slams into our magnetosphere, the charged particles are deflected and funneled toward the poles. As those particles bleed into the upper atmosphere, they collide with oxygen and nitrogen. The resulting atmospheric collision paints the night sky with the glowing green ribbons of the aurora borealis. Protected by this magnetic deflection, the surviving light and heat filter down to the surface in a steady, regulated dose, by powering photosynthesis, driving global weather patterns, and warming the oceans. But our modern technological civilization has introduced a new vulnerability. The invisible radiation carried by the solar wind creates space weather, and it poses a direct physical threat to our electronics. If a severe coronal mass ejection were to strike Earth directly today, the resulting magnetic storm could induce massive electrical currents in our power grids, blowing out transformers and permanently crippling communication satellites. To understand and predict this threat, space agencies have deployed highly specialized missions. Spacecraft like NASA's Parker Solar Probe actually fly directly through the sun's superheated outer corona to sample the solar wind at its source. Global efforts are expanding this early warning network. Launches like India's Aditya L1 observatory position specialized instruments in space to monitor incoming solar storms before they reach Earth. Protecting our digital infrastructure now requires a constant watch on stellar mechanics. Monitoring the volatile moods of the sun has become a functional necessity for maintaining the power and communications that sustain modern life. Eventually, the delicate balance of this nuclear engine will fail. Roughly 5 billion years from now, the sun's core will exhaust its supply of hydrogen fuel. This model illustrates how the core will contract while the outer layers expand uncontrollably. The sun will swell into a monstrous red giant, growing so massive it will swallow Mercury, Venus, and likely Earth. Unable to hold on to its own mass, the dying star will eventually puff away its outer layers, leaving behind a glowing, expanding cloud of gas known as a planetary nebula. All that will remain at the center is the exposed core, a small, incredibly dense white dwarf, slowly radiating its residual heat into the dark for eternity. The star at the center of our system has a strict, finite lifespan. Its death dictates the ultimate expiration date for everything caught in its gravitational pull. Today, we sit in a miraculous window of stability. The sun is a terrifying, violent nuclear engine, violently burning through its own mass. Yet that continuous destruction provides the exact conditions necessary for the oceans to flow and for life to thrive. But not every planet is so lucky. In the next episode, we'll leave the safety of Earth's magnetic shield and travel to the scorched, barren world that sits closest to the blast radius, Mercury. In this view from the space station, the sun rises over the Earth's curved horizon as a bright, static orb. From the surface, we often view our star as a giant, uncomplicated campfire burning steadily in the vacuum of space. But the warmth reaching Earth right now is actually ancient. This energy fought a brutal, agonizing battle to escape its source. Understanding our solar system requires looking past that image to see the sun as a complex, layered machine. To trace the true nature of sunlight, we have to travel back to where it is born, diving deep inside the star itself. We have to penetrate thousands of miles of dense, roaring layers of plasma, pushing past the visible surface and driving deeper toward the absolute center. Down here, the environment shifts into a realm of crushing gravitational pressure and intense heat, entirely hidden from the outside world. It is the most extreme and isolated environment in our solar system, yet it serves as the hidden engine that sustains all life on Earth. This is the core. Here, temperatures reach 15 million degrees Celsius. Under this immense pressure, hydrogen atoms are forced together. They merge to create helium, releasing a concentrated burst of energy outward. This reaction happens at a massive scale. The sun converts roughly 600 million tons of hydrogen into helium every single second. This raw, newly forged energy is the nascent form of the sunlight we will eventually see. Without this continuous, violent fusion process pushing outward from the core, the star would collapse under its own gravity, and the solar system would freeze. That energy has to cross the radiative zone, the incredibly dense layer immediately surrounding the core. But it faces a severe physical barrier. The solar plasma here is so thick that the energy cannot travel in a straight line. Instead, it undergoes what scientists call a random walk. A single photon bounces chaotically, constantly ricocheting between closely packed plasma particles. Because of this zigzagging path, it takes anywhere from thousands to hundreds of thousands of years for a single photon to clear this one zone. The light warming you today was trapped inside this dense layer long before human civilization existed. Eventually, the energy reaches the convective zone, the outer interior layer, where the plasma density finally begins to drop. Here, the transportation mechanism shifts. The energy no longer bounces from particle to particle. It hitches a ride on massive swirling rivers of superheated plasma. This diagram illustrates those convection currents. Hot plasma rises toward the surface, carrying the energy, while cooler plasma sinks back down, mimicking the cycle of boiling water. After millennia of being trapped in the dense layers below, this violent churning rapidly accelerates the outward journey. This boiling motion is the final mechanism. It physically ferries the trapped energy up from the depths and delivers it to the threshold of empty space. This image reveals the photosphere, the 5,500-degree visible surface where the energy finally erupts into view. This surface is not perfectly uniform. It is marked by cooler, magnetically active regions known as sunspots. Just above the surface sits the chromosphere, visible in this eclipse photograph as the pinkish solar prominences along the edge of the moon. Beyond that is the corona. This bright white halo is a massive outer atmosphere stretching millions of kilometers into space. These bright golden magnetic loops showcase the violent activity that drives a major scientific anomaly. The corona is significantly hotter than the visible surface below. Escaping the star's dense interior was only the first step. The energy must navigate this chaotic, magnetically superheated atmosphere to finally break free. Once it clears the sun's magnetic grip, the energy rockets across the vacuum of space directly toward our planet. This light reaches us only after moving through a fusion reaction of the core, a 100,000-year trap of density, and a boiling river of plasma. The sun operates as a perfectly balanced stellar engine. Every ray of sunlight reaching Earth has endured this specific, multi-layered journey out of the interior. To truly understand our solar system, we have to look closer at the mechanism driving this journey. Next time, we explore nuclear fusion.
From our perspective on Earth, the sun appears as a steady, reliable furnace, a power plant that has burned continuously for over 4.5 billion years. But this creates a scientific contradiction. Between us and that light lies the near-total vacuum of space, a void containing no oxygen at all. Without oxygen, there can be no combustion. There is no coal, no traditional fuel, and not a single actual flame on the sun's surface. Because fire is physically impossible in this environment, the sun must be driven by a hidden, vastly more powerful mechanism. To find that mechanism, we have to leave the surface and plunge toward the core, past the boiling, turbulent layers of the star's interior. We are entering the core, the single most extreme environment in the entire solar system. The conditions at this depth are so far removed from our everyday world that they provide the only explanation for how a star actually functions. In this inner sanctuary, temperatures reach a staggering 15 million degrees Celsius. Above us, the weight of the entire star creates a crushing gravitational pressure that reaches unimaginable levels. This pressure is so intense that atoms can no longer maintain their standard structure. Moving through this dense chaos is the sun's primary fuel, a sea of rapidly vibrating hydrogen nuclei. In any other environment, these particles would repel one another, but here they are forced to collide and merge. This forced atomic merger is nuclear fusion, the fireless engine that powers the stars. This process follows a precise recipe. 4 hydrogen nuclei are pressed together, fusing into one helium nucleus. But the math doesn't add up. The resulting helium nucleus weighs less than the 4 original hydrogen atoms combined. A tiny fraction of mass has vanished. This missing matter was not destroyed. Instead, it has been perfectly converted into pure radiant energy. This conversion was the great discovery of Albert Einstein, who proved that matter and energy are simply different forms of the same thing. He defined this relationship through the equation E equals mc squared, the mathematical rulebook for everything happening inside the sun. To maintain its glow, the sun merges 600 million tons of hydrogen every single second. In that same second,
Nearly 4 million tons of physical matter are successfully transformed into light. The sun's power is the result of its own substance being systematically turned into energy, second after second, for billions of years. Once created, these photons begin their escape from the core. Because the interior is so dense, the energy must bounce and struggle through the star's inner layers for millions of years before it can reach the surface. Finally, the energy breaches the solar atmosphere, escaping the star's gravity at last. The photons are launched into the vacuum of space, traveling at the speed of light toward a distant blue planet. Across the solar system, it is a rapid sprint, only 8 minutes and 20 seconds from the Sun to the Earth. The light spent millions of years trapped inside the star, only to cross the final 93 million miles in less than 10 minutes. This ancient energy arrives at our world as gentle sunlight. It is the force that warms our oceans, dictates our weather, and fuels the growth of every forest on Earth. The warmth of a sunrise is the final act of a process that 93 million miles away, preparing to unleash explosive storms and solar flares that can threaten the very technology we rely on.
From 93 million miles away, the sun is a quiet, steady companion in our sky. It rises, it sets, and it bathes our planet in a consistent, life-giving glow. But if you travel across that immense stretch of space and approach the star itself, that peaceful illusion instantly shatters. Up close, there is no solid surface. Instead, you face a boundless, violent ocean of fire, where superheated plasma churns at 10,000 degrees. This visible outer layer is called the photosphere. It is the final boundary where the star's heat and light manage to escape into the vacuum of space. Yet what bubbles on this layer is only the exhaust of a much larger engine. Millions of miles below, the star's core generates immense, crushing outward pressure. The sun is an active, magnetically driven nuclear reactor, locked in a perpetual, violent struggle to contain its own internal energy. That internal struggle cannot stay hidden forever. In specific areas, intense magnetic pressure forces its way right through the photosphere. Looking near the curved edge of the star, you can see these dark blemishes disrupting the blindingly bright plasma. These patches are known as sunspots. They appear dark to our instruments because localized extreme magnetic fields choke off the heat rising from below, forcing the surface temperature to drop. That drop is entirely relative. Even these cooled, shadowy zones burn at roughly 7,000 degrees Fahrenheit, hotter than any natural environment on Earth. These sunspots act as the physical anchors of twisting, coiling magnetic tension, functioning as reservoirs of trapped kinetic energy that wind tighter by the hour. Invisible lines of magnetic force stretch high above these sunspots, twisting into complex knots until the plasma simply cannot bend any further. When those lines finally snap, the stored energy detonates in an instant. This eruption is known as a solar flare. A blinding, cross-shaped burst of high-energy X-rays and charged particles is violently hurled outward from the detonation site. In a matter of seconds, this highly localized blast releases the equivalent energy of several billion nuclear bombs detonating all at once. While the initial flash of the flare is pure radiation, the explosion also rips physical matter straight out of the star. These glowing currents of superheated plasma that rise from the blast zone are called solar prominences. Tethered to invisible magnetic tracks, they form massive wispy arches reaching high into the dark void of space. A single one of these glowing arches could easily encompass a stack of several Earth-sized planets, extending hundreds of thousands of kilometers into the solar atmosphere. For days at a time, these prominences function as immense cages, trapping millions of tons of boiling material suspended in the vacuum above the sun. Eventually, the kinetic fury of the trapped plasma becomes too great for the magnetic cage to hold. Without warning, the loop violently ruptures, shedding its captive material. This triggers the ultimate solar weather event, a coronal mass ejection. This specialized satellite image captures a massive, bright red cloud of plasma bursting radially outward. To expose the true scale of the surrounding eruption, the instrument uses an occulting disk, the dark central circle you see here, to block the blinding light of the sun's core. Once the superheated cloud fully detaches, it rapidly accelerates into the vacuum, carrying billions of tons of dense, highly charged particles. These immense storms do not simply dissipate into the void. They barrel across the solar system at millions of miles per hour, dictating the space weather and presenting a severe direct threat to the atmosphere and technology of any planet caught in their path. On a clear afternoon, the sun appears as a steady, quiet sphere of light, reliably providing the energy that sustains life on our planet. But beneath that bright, even surface, pools of superheated plasma generate a chaotic, twisting web of intense magnetic energy. When these tangled magnetic field lines wind too tightly, they reach a breaking point. They snap without warning, releasing enormous amounts of pent-up energy. This single fracture turns a quiet star into an active threat, putting any planet caught in the crossfire at immediate risk. The snapping of those magnetic lines triggers a massive explosion, an event known as a coronal mass ejection, or CME. The force of this blast tears material directly from the sun's corona, launching billions of tons of supercharged plasma into the vacuum of space. This dense cloud of atomic particles accelerates rapidly, reaching velocities of millions of kilometers per hour. While these eruptions often fire into empty space, this specific billion-ton cloud of plasma is aimed directly at Earth. Moving at these extreme speeds, it will cross the inner solar system in 1 to 3 days. A countdown has started. A localized disturbance on the surface of our star has become an imminent planetary threat. The plasma cloud travels in total silence, crossing the 150 million kilometers of empty space, separating the sun from our planet. This cloud functions as a self-contained magnetic storm, hauling embedded magnetic field lines and charged particles through the void. As it moves from the sun, the cloud balloons in size, stretching millions of kilometers across. On Earth, the 72-hour window closes as the leading edge of the storm enters our immediate cosmic neighborhood. Impact is imminent. Earth faces an overwhelming, invisible wall of magnetic energy. Traveling at peak velocity, the front of the solar storm finally slams into Earth's orbital path. The solar storm crashes directly against Earth's unseen armor, a protective barrier known as the magnetosphere. The magnetosphere absorbs the brute force of the impact, acting as a planetary shock absorber as its outer layers compress backward toward the atmosphere. That compression pushes back, deflecting the blast and washing the majority of charged particles around the sides of the planet. A fraction of particles are trapped by field lines and funneled into the polar regions. Without this magnetic defense successfully repelling the storm, the solar wind would eventually strip away our atmosphere, leaving Earth barren. When those funneled particles strike the gases in our upper polar atmosphere, they ignite in a display of light, the aurora borealis and aurora australis. For a brief moment, the violence of a cosmic impact is translated into a silent atmospheric light show. But the danger persists. While the atmosphere shields the surface, the electromagnetic shockwave from the CME disrupts the space environment around the planet. This creates hazards for our technology in orbit, potentially overwhelming sensors and blinding the satellites we rely on for global infrastructure. Those orbital disruptions quickly cascade to the surface, scrambling radio communications and disrupting global GPS navigation. In extreme cases, fluctuating magnetic fields induce rogue electrical currents in the ground, threatening to overload and blow out segments of the electrical grid. Our biology is protected by the magnetosphere, but our heavy reliance on sensitive electronics leaves our civilization exposed to this solar force. To defend against these impacts, international space agencies rely on a network of observatories, acting as our cosmic meteorologists. By tracking the sun's magnetic activity, scientists detect eruptions as they occur, providing the early warnings needed to secure power grids before a major storm hits. This reminds us that despite 150 million kilometers of space, our lives remain bound to the moods of our nearest star. But if an eruption causes this much chaos in a few days, it raises another question. What invisible forces are flowing over Earth during the long stretches when the sun is quiet? Look up at the night sky. and it's easy to imagine the space between the planets as a silent, dead vacuum, with the sun sitting in the center like a static light bulb. But that quiet image is an illusion. Our cosmic neighborhood is actually a violently active environment, washed in a constant, high-speed storm. The sun is continuously exhaling. It blasts millions of tons of superheated material from its outer atmosphere directly into the dark void every single second. Because of this continuous eruption, Earth and every other planet sit directly in the crosshairs of a relentless, inescapable wave of stellar material. Astrophysicists call this endless stream of charged particles the solar wind. To understand its sheer force, let's look at velocity. This chart compares a high-powered rifle bullet to the solar wind. A bullet travels roughly 1 kilometer per second. The solar wind races outward at an astonishing 400 to 800 kilometers per second. If a planet were left fully exposed, this high-energy plasma would bombard the surface, slowly and violently stripping away any atmosphere, molecule by molecule. Which raises an obvious question. If we are facing a continuous, highly charged barrage from our own star, how exactly does life on Earth survive? As the outward radiation leaves the sun, it first washes over Mercury, baking the planet's completely barren, unprotected, moon-like surface. The wave continues outward, slamming next into Venus, where the charged particles interact heavily with its dense, swirling layers of cloud cover. Then it arrives at Earth. Here, our vibrant blue planet sits directly in the path of the oncoming solar storm. But Earth has an invisible defense system, the magnetosphere. It's a massive magnetic field acting as a physical barrier in space. As the charged solar wind strikes this barrier, the field forces the dangerous plasma to flow harmlessly around the planet. Without this invisible deflection, the solar wind would scour away our atmosphere, and the conditions necessary for life would cease to exist. However, the magnetosphere isn't a solid, perfect sphere. Its structure naturally forms funnel-like weak points near the north and south poles. A fraction of the high-speed solar plasma slips through these polar funnels, crashing violently into oxygen and nitrogen molecules in our upper atmosphere. This high-speed impact releases massive energy, instantly illuminating the sky with vast ribbons of light. In the northern hemisphere, we see the result of this collision as the aurora borealis, painting the Arctic skies in vivid greens and reds. In the southern hemisphere, its counterpart, the aurora australis, shimmers over the Antarctic and coastal regions. These dancing lights are beautiful, but they are literally the visible, glowing footprints of a high-energy cosmic collision. But the aurora only accounts for a tiny fraction of the solar wind. The vast majority of the plasma bypasses Earth entirely, continuing its high-speed race into the dark. It sweeps past the dusty red plains of Mars, unhindered by its thin atmosphere. It travels billions of miles further outward, washing over the massive gas giant Jupiter and its complex system of moons. Finally, the particles reach the outer edges of the planetary system, rushing right past the frozen blue expanse of Neptune. Even this incredibly far from the warmth of the sun, the solar wind is still moving outward, building towards its most important purpose at the very edge of interstellar space. Eventually, the expanding solar wind reaches a point where it pushes against the cold, dense gases of the interstellar medium, forming a colossal bubble. Astrophysicists call this massive boundary the heliosphere, and it fully encloses all the planetary orbits within its glowing balloon-like wall. Beyond this wall lies deep space, which contains highly lethal cosmic rays, subatomic fragments blasted outward by ancient supernovas in the broader galaxy. The heliosphere acts as a macro shield. As dense interstellar cosmic rays strike the outer edge of this boundary, they bounce off, violently repelled away from our planetary neighborhood. The sun provides us with light and heat, but through the endless outward flow of the solar wind, it actively connects and protects every single world in our cosmic home. Switch off the star at the center of our system, and the planet freezes. Within days, surface temperatures drop low enough to lock the oceans in solid, creeping ice. Eventually, the atmosphere itself collapses, freezing and falling to the ground as snow. We inhabit an incredibly fragile oasis, suspended in a cosmic vacuum that is permanently pitch black and absolute zero. The mechanism keeping this world from reverting to a frozen rock is located roughly 150 million kilometers away. Across that immense empty gap, the sun pumps out raw stellar radiation. It travels through the vacuum of space, making contact with the Earth's upper atmosphere. Once this radiation arrives, it acts as the ignition source for everything that happens on the surface. It provides the raw physical fuel for every biological process and atmospheric cycle we experience. A sunrise is a daily fuel delivery system. It is the exact injection of energy required to prevent our biological and physical systems from collapsing into the cold void. As that raw sunlight pierces the atmosphere and hits the ground, it interacts directly with the biosphere. Plants have evolved a highly specific mechanism to capture this arriving radiation. Through photosynthesis, they act as living solar panels. To run this process, a plant pulls in water from the soil and carbon dioxide from the surrounding air. The incoming stellar radiation acts like a hammer, breaking these molecules apart. The energy then forces the scattered atoms to recombine into entirely new structures, specifically glucose and oxygen. The oxygen is released back into the atmosphere for us to breathe, while the glucose remains trapped inside the plant as stored foundational food energy. When an animal eats the plant, it absorbs that trapped solar energy. A bird catches an insect, a whale consumes plankton. The original radiation simply transfers up the entire food chain. Every muscle contraction, every heartbeat, and every breath taken by a living creature is powered by successfully stored sunlight. On a planetary scale, the sun's thermal energy strikes the open oceans and immediately begins to heat the surface water. This intense heat physically lifts millions of tons of liquid water into the air, transforming it into vapor. As this vapor rises and cools, it gathers into massive cloud systems. These systems are pushed inland, eventually dropping that moisture over mountains and forests as rain, driving the entire global water cycle. Because the Earth is a sphere, the sun heats its surface unevenly. The equator bakes, while the poles remain frozen, creating massive pressure differences across the atmosphere. Cold air rushes in to replace rising warm air. This constant balancing act generates global wind patterns and drives the churning engine of our ocean currents. The changing seasons, a gentle breeze, and a Category 5 hurricane are all driven by the exact same source. Our weather is simply the kinetic expression of solar heat. For millions of years, the planetary energy chain operated without us. Now, humanity has introduced a new variable. Historically, we relied on digging up ancient buried solar energy in the form of fossil fuels. Today, we capture the radiation directly as it hits the ground. Massive arrays of photovoltaic panels intercept the sunlight before it can hit the Earth. The incoming photons knock electrons loose within the panels, converting the light straight into clean, usable electrical current. That current is fed into the grid, routed through transmission lines, and delivered to power hospitals, schools, and entire cities. We are entirely bypassing the biological middleman. We no longer need to wait for plants to grow, or for matter to fossilize to access the star's power. By pulling electricity straight from the sky, we are forging a self-directed, cleaner energy future for our species. When you pull back and look at the Earth and the sun together, the unbreakable lifeline becomes clear. The food we eat, the rain that fills our lakes, and the electricity powering our devices are all different incarnations of transformed sunlight. But this engine is running on a finite supply of hydrogen fuel. It cannot burn forever. The deep stability that has allowed life to thrive on Earth for billions of years has an expiration date. Eventually, the sun's core will exhaust its fuel. When that happens, the star will violently expand into a red giant, swelling outward and threatening to completely consume the inner planets in fire. The sun sustains every passing moment of our present, and our ultimate planetary fate remains permanently locked to the inevitable evolution of our nearest star. For as long as humanity has looked upward, the sun has been a constant anchor. It rises, it sets, and it reliably warms our world. Astronomers classify our local star in its current phase as a main sequence star, marking the most stable period of its life cycle. This ultraviolet image captures the extreme, blazing reality of the sun's surface. Every single second, it detonates millions of tons of matter, generating the massive gravitational and magnetic forces required to hold the entire solar system together. It has maintained this blistering output for approximately 4.6 billion years. Yet despite its seemingly eternal presence, the stable star we orbit today is only halfway through its story. The sun is, at its core, a mechanical engine, and like any engine, it relies on a finite supply of fuel, in this case, immense reserves of hydrogen gas. Based on its mass and burn rate, astronomers calculate that the core holds enough hydrogen to keep the star stable for about 5 billion more years. Once that specific supply of hydrogen runs dry, the delicate gravitational balance holding the inner planets in their peaceful orbits will unravel. To understand the fate of our solar system, we must accelerate our perspective forward through deep time, billions of years past the present day. The death of our star is a mechanical certainty, dictated entirely by the strict laws of stellar physics. Right now, the sun is locked in a perfect standoff. The immense inward crush of its own gravity is countered exactly by the outward pressure of nuclear fusion radiating from the core. When the last of the core's hydrogen fuses into helium, that outward pressure will drastically drop. Without the push of fusion to hold it up, gravity will instantly win the standoff, violently crushing the star's core inward on itself. As we can see in this diagram, the inward crush of gravity overpowers the fading fusion. This extreme compression forces the matter inside the core to pack tighter and tighter, driving its internal temperature to blinding extreme levels. A star does not die by quietly cooling down. Its final collapse begins as a superheated, intensely burning furnace. This intense heat radiating from the dying core pushes against the star's outer layers of gas, forcing them to swell aggressively outward into space. The sun will expand to hundreds of times its current size, entering a phase astronomers classify as a red giant. As the star swells, its outer boundaries will physically engulf the orbits of Mercury and Venus, incinerating both planets entirely. The sheer intensity of the expanding solar radiation will boil away Earth's oceans and strip the atmosphere into the vacuum of space. The planet we inhabit today will be reduced to a completely barren, heavily irradiated globe of melted rock. The very star that provided the warmth and energy necessary for biology to flourish will ultimately sterilize the world it nurtured. The red giant phase will burn intensely for millions of years, but the star cannot sustain its massive, bloated size forever. Eventually, the dense core will no longer generate enough gravitational pull to hold onto its vastly expanded outer atmosphere. The outer layers of gas will gently detach from the core, drifting outward in all directions. These illuminated shells of expelled gas will form a massive, brilliantly colored structure known as a planetary nebula. The violent destruction of the inner solar system ultimately gives way to a sprawling, illuminated cloud of stellar material, visible for light years across the galaxy. Deep inside the center of this expanding cloud of gas, a single object remains. Stripped of its atmosphere, the exposed core is incredibly dense and emits a piercing, intense heat. This dead stellar remnant is called a white dwarf. This scale comparison illustrates the sheer density of the remnant. It contains half the total mass of the original sun, yet it is crushed down into a sphere roughly the exact size of the Earth. The immense star that once dictated the movements of the entire solar system is reduced to an ember no larger than the planet it destroyed. Over the next tens of billions of years, the white dwarf will slowly radiate away its remaining heat, fading into total darkness. Meanwhile, the planetary nebula continues to drift outward, carrying with it complex, heavy elements forged inside the dying star. These heavy elements will eventually collide with other interstellar clouds, providing the raw material necessary to form new stars and new rocky planets. The destruction of our solar system acts as a mechanical distributor, supplying the galaxy with the chemical ingredients required for future life. But we do not have to wait 5 billion years to understand the mechanics governing our star. This photograph shows the Solar and Heliospheric Observatory, or SOHO, in a clean room, part of an ongoing engineering effort to monitor our sun today.
Here, the nighttime launch of the Parker Solar Probe marks the explosive beginning of an ambitious mission to physically fly through the Sun's outer atmosphere. Space agencies worldwide are joining the effort. Launches like this one, carrying India's Aditya L1 observatory alongside Europe's solar orbiter, complete a comprehensive surveillance network. In our next episode, we will follow these machines into the extreme heat of the inner solar system to uncover the active daily mechanics of the star that dictates our existence.
For most of human history, our relationship with the sun was defined by a distance we could not cross. We were restricted to observing its influence from the Earth's surface. Ancient civilizations built massive stone monuments to track its movements with precision, yet the star itself remained an untouchable, distant force. Even as our technology advanced and we built sophisticated modern observatories, the 150 million kilometer physical gap between Earth and the Sun remained a barrier to direct study. We now know that this distance is deceptive. The Sun generates volatile magnetic storms and space weather that can strike our atmosphere, threatening the electrical grids and satellites our modern world depends on. The source of this volatility is the corona, the Sun's outer atmosphere. Historically, this region was a mystery that we could only witness during the few minutes of a total solar eclipse. To protect our infrastructure and solve the mystery of the corona, we had to move beyond passive observation and begin the journey toward the fire. The first phase of this exploration involved launching observation platforms into orbits that are entirely free from the interference of Earth's atmosphere. These missions target the Sun-Earth L1 point, 1.5 million kilometers closer to the star. Here, equalized gravitational pulls allow spacecraft to hover stably. This location is occupied by SOHO and Aditya L1. From here, they maintain an unobstructed view of the Sun, never entering Earth's shadow. They act as sentinels, analyzing the incoming solar wind and magnetic particles minutes before they reach our atmosphere. By maintaining this presence at L1, we have established our first defensive early warning system against solar activity. While the L1 point provides a constant view, scientific necessity pushed us to design missions that could travel much closer to the Sun's actual surface. The Solar Orbiter is the result of that effort, a probe built to survive an eccentric orbit that brings it within 42 million kilometers of the star. To meet its primary objective, the mission will use gravitational assists to shift off the standard planetary plane, allowing its cameras to look directly down at the Sun's north and south poles. This unique perspective provides high-resolution data on the magnetic loops and solar flares that emerge from the polar regions, impossible to see from Earth. By changing our physical perspective in space, the solar orbiter allows us to study the magnetic shifts that drive the Sun's 11-year activity cycle. To truly understand the corona, we had to go further than imaging. We had to build a machine capable of entering the solar atmosphere itself. NASA's Parker Solar Probe was the mission designed to bridge that final gap and reach the star's outer atmosphere. To maintain its orbit, the probe must move at nearly 700,000 kilometers per hour, making it the fastest human-made object in history. Protection comes from a carbon composite heat shield. It withstands temperatures of 1,300 degrees Celsius, keeping the instruments behind it at a temperature comparable to a typical office. Parker is currently flying through the corona, sampling the charged particles and magnetic fields at their point of origin. By sampling this environment directly, we have replaced distant theories with actual measurements from the most hostile region in the solar system. If we look at the inner solar system as a single environment, we can see how our presence has changed. Parker, Solar Orbiter, SOHO, and Aditya L1 now function as a synchronized network of sensors distributed across millions of kilometers. By placing these machines in strategic positions, we have extended our reach far beyond the limits of Earth's atmosphere. The data they provide allows us to better predict solar behavior, giving us the lead time necessary to protect the technology and power systems that sustain modern life. Suspended in the vacuum of space, our planet lacks the internal heat or light required to sustain life on its own. It relies entirely on an external engine to keep its oceans liquid and its atmosphere in motion. Down on the surface, the results of that energy are visible everywhere. Dense forest canopies capture radiation for photosynthesis, while the thermal contrast across ocean horizons drives global weather patterns and ocean currents. Every physical movement in this environment, from the circulation of the jet stream to the caloric energy burned by wildlife, can be traced back across 93 million miles of empty space to a single, continuous light source. Without this constant influx of radiation, global temperatures would plummet within days, the oceans would freeze solid, and the biosphere would cease to function. Close-up observation reveals that this source of warmth is an intensely violent nuclear reactor. The surface is a chaotic landscape of superheated plasma, where immense magnetic fields constantly twist and snap. Look at the scale comparison. A single erupting prominence of magnetized plasma, like the one arching out here, frequently extends hundreds of thousands of miles into space, dwarfing our entire planet many times over. Beyond its outward glow, the sun is a dense sphere of hydrogen and helium, crushing millions of tons of matter every second to forge raw energy. The stability of life on Earth depends on a precise thermal balance provided by a star that is, by its very nature, violently unpredictable and magnetically unstable. This cross-section details the sun's internal structure. Extreme pressure and heat at the center force hydrogen to fuse, releasing photons. These photons begin a grueling journey outward. When they finally break the surface, magnetic field lines can snap, triggering violent surface explosions. These detonations regularly launch coronal mass ejections, billions of tons of charged solar material, accelerating outward into the vacuum of space at high speed. As this material travels, it generates a highly turbulent environment of solar wind that constantly washes over the 8 planets, threatening any world that lacks a strong magnetic shield to deflect the radiation. The sun's volatile weather system constantly bombards the solar system, making the survival of life on Earth a continuous, precarious balance. To map this unpredictable space weather and secure our modern technological infrastructure against solar storms, observation from Earth is no longer sufficient. We have to send instruments directly into the radiation zone. Escaping Earth's gravity to drop a payload toward the center of the solar system requires immense physical effort and heavy lift rocketry. Leading this effort is NASA's Parker Solar Probe. Its specialized carbon composite shield is designed to fly through the sun's outer atmosphere, withstanding extreme temperatures. Partnering in this orbital fleet, the ESA Solar Orbiter uses complex gravity assists to capture high-resolution imagery of the sun's unmapped poles. They join veteran hardware like the SOHO observatory, which uses heavy shielding to monitor solar radiation and track incoming coronal mass ejections. Global investment in this research continues to expand. India recently launched its historic Aditya L1 mission to study the solar atmosphere from 1 million miles away. The telemetry from this combined international fleet streams back to server farms on Earth, where analysts track magnetic fluctuations to provide early warnings for solar storms before they can impact our satellite networks or power grids. These missions provide the granular data needed to refine our models of solar activity, helping us better predict how this nuclear reactor will behave next. But despite its overwhelming mass and extreme energy output, the sun's supply of hydrogen is finite. In roughly 5 billion years, the fusion engine at its core will exhaust its fuel. This animated map illustrates the vast gravitational grip that the sun maintains over its system, anchoring the terrestrial inner worlds and the outer gas giants into a single, cohesive orbital structure. Yet, when you scale out to the wider galactic neighborhood, our entire system, along with its central star, shrinks down to a microscopic speck of light, drifting among hundreds of billions of other stars in the Milky Way. Deconstructing how the sun both threatens and sustains our planet is an essential baseline. We must thoroughly map our local star before accurately evaluating the conditions around distant exoplanets. The data gathered by these solar probes and orbital observatories is actively laying the groundwork for our long-term survival off-world. We have steadily engineered the capability to sustain human life in the vacuum of space, continuously pushing our operational boundaries further outward from Earth's atmosphere. But to truly comprehend the raw power of the solar environment, we must observe planets that formed deep inside the sun's direct radiation zone. That requires shifting our focus inward, past Venus,
to examine the desolate, cratered rock that orbits closest to the solar surface. The mapping of our solar system is an ongoing process. If you want to follow the data as we move inward, make sure to subscribe, because our next expedition will take us directly to Mercury, the scorched world.
Knowledge changes lives. Technology shapes the future. And curiosity drives human progress.
Welcome to a place where science, space, artificial intelligence, engineering, and innovation come alive.
From the mysteries of the universe to tomorrow's groundbreaking technologies, every video is designed to inspire, educate, experience Hollywood-quality documentaries with breathtaking visuals, powerful storytelling, and easy-to-understand explanation. Subscribe today and become part of a global community that believes learning never stops. This is more than a YouTube channel. This is the future of learning. American Education Tech. Explore, discover.